Okay. Are you able to see this slide?
Yes, sir.
Yes, sir.
Okay. So last class we are looking at this. That is how to represent the parabolic penalty function numerically. Okay. So this is the representation of parabolic penalty function, and this is the combined expression. That is objective function plus r into this penalty function. So we found that for parabolic penalty function, it will convert at large values of r. So what is large values of r? Is it 100, 1000, 10,000, etc.? So we don't know. So we give a small values of r and slowly increase it. Okay, 10, 100, 1000, etc. We try all these values of r and we see at which value of r convergence occurs. Okay, and at every step we have to check for constraint violation and also the value of the penalty. Penalty is this thing. Okay, penalty of this, and constraint violation is you have to substitute x and y in this equation and find this value, and it must be equal to 0 if there is no constraint violation. So next we look at convergence of inequality constraint penalty functions. That is penalty functions of the type absolute value of gx or g of x the whole squared. So how does their convergence look like? So the mathematical proof of their convergence is very difficult, but it can be shown that both these penalty functions will converge to the optima at large values of r. So their behavior is similar to the parabolic penalty function. So you have to try small values of r and step by step increase it and check the convergence of the solution and also check the penalty. So these two penalty functions behave in the same manner as parabolic penalty function. So we will not look further into that. We can accept it as it is. Next, convergence of log penalty function and reciprocal penalty function. So log penalty function is minus r log into, minus r log of g of x, and this reciprocal function is 1 by g of x. Okay, so the logic is that this 1 by g of x will tend to infinity. Okay, at the boundary. Okay, and also minus log g of x will also tend to infinity. So the value of r must be small enough to neutralize this infinity so that it becomes a finite value. Okay, so let us look at a simple example of implementing the logarithmic penalty function. So this is the same problem, that is minimize this objective function subject to this inequality constraint. So you can see the graphical image here, and you can see that the actual solution is 2.5, 2.5. This is the unconstrained minimize here. Okay, unconstrained minimize here, that is 4, 4, and constrained minimize 2.5, 2.5. So use log penalty function. Okay, so we already saw that if you want to use the log penalty function, then the equality constraint must be written in the greater than or equal to 0 form. Okay, so x plus y minus 5 is less than or equal to 0. Minus x minus y plus 5 is greater than or equal to 0. And that is inserted here as a penalty function. That is minus r into log of minus x minus y plus 5. Okay. So now equating the partial first derivative to 0 of the combined objective function. The partial q by partial x equal to 0, partial q by partial y is equal to 0. So the two equations are there and three unknowns are there. Okay, but luckily these two equations are symmetric in x and y. Okay, so x and y are symmetric. Okay, or x and y can be interchanged. So that means x is equal to y. Okay, so what you can do is that you can ignore one of this, and here instead of y you put x. Okay, so 2 into x minus 4 plus r by 5 minus 2x is equal to 0. Okay, so if you solve this equation, now this will become a quadratic equation. You will get two values of x, that is 13 by 4 plus or minus 9 plus 4r by 16. Two values of x are obtained. So you can see that when r tends to 0, okay, you will get one of the solution, one of the values of x will be 2.5, 2.5. Okay. Okay, I think that is the plus value or something. Okay, plus value or minus value? Minus value. Okay, minus will give the correct answer, and the other value of x, okay, will violate the constraints. So from this simple example, we can see that generally for logarithmic functions, we get the correct solution when r tends to 0. Okay, so that is the tip we have obtained from this simple analysis. Okay, so generally for log functions, small value of r gives the correct result. And also at every step you have to check the constraint violation and the penalty. Okay, so how do you numerically implement this log penalty function? Okay, so what you see here is the graphical representation. This is the correct answer. So we'll have a starting point -3, which is inside the feasible region. Okay, because log penalty works only inside the feasible region. Okay, so you have to write the expression for the combined objective function q, that is f of xy plus, minus r into log of g of x. Okay, so this is f of xy, this is minus r into log of g of xy. Okay, so you can solve this by any unconstrained numerical algorithm like Cauchy's method or Fletcher's method or any other method. Okay, so if you solve it with this starting point of -3, okay, then the first solution we get is -1.8, -1.8. Okay, so you have to check the constraint violation and penalty at -1.8, -1.8. So first let us check this constraint. Okay, so -x minus y plus 5 should be greater than or equal to 0. Okay, so minus 1, so plus 1.8, plus 1.8. Okay, so okay, plus 1.8 plus 1 plus 5 is greater than or equal to 0. So constraint is not violated. Okay, but the penalty term is large. Minus r log into this term is very large. Okay, so this step is wrong because although constraint is not violated, penalty is large. Okay, then next you use this as a starting point. Okay, for next step of solution, xy equal to -1.8, -1.8 is the starting point. You put r equal to 10. Okay. Okay, so in this log penalty function, R will work for very small value. So what is very small value? Is it 0.1 or 0.001 or 0.0001? We don't know. So what you do is that you start with large values of R, successively decrease it. Okay, 0.1, 0.001, 0.0001, etc. And you check at which values of R it will converge. So first we tried R equal to 100, it is not working. Next we put R equal to 10. So we get next solution as x2y2 is 1.5, 1.5. Then penalty has come down to minus 6.931. Okay. And constraint is not violated. Okay, next R equal to 1 is tried. Then R equal to 0.001 is tried. So you can see that penalty is becoming small and the XY value is converging to 2.5, 2.5. And the constraint is not violated. So 3 parameters need to be tracked. Okay. 3 parameters need to be tracked. Okay, first is the convergence, next is the penalty violation. Penalty value, and the third is the constraint violation. So all 3 are satisfied or beginning to be satisfied when R equal to 0.001. Okay. So the penalty term minus R into log of gx diminishes to 0 at the optimum. Okay, so next we'll investigate the reciprocal penalty function. So that also we know it will converge at small values of R. So you have to start at large values of R and slowly decrease it to find which value of R it converges. Okay. Okay, so this is the combined objective function plus penalty. So the penalty term. Okay. So, if it has to be an optima at x star y star, then partial q by partial x equal to 0, partial q by partial y equal to 0, and you have to equate both of them. Okay, and because these equations are symmetric in x and y, you can replace y with x or x with y. So you can put x equal to y in this equation. Okay, so 5x, so 5 minus 2x. Okay, so you can ignore this and to solve this. Okay, so you will get to an equation like this. Okay, you will get a cubic equation. So it can be shown that one solution is xy equal to 2.5, 2.5. So if we look at this term, okay, when x is equal to 5 by 2, then this term will become 0. Okay, so one solution of this thing is that when x is that is when r tends to 0, x will be equal to 5 by 2. Okay, when r tends to 0, then x is equal to 5 by 2 is a solution. The implementation of reciprocal penalty function. Okay, so first you have to write this combined objective function q of x. Okay, so objective function plus penalty term. Okay, so in this method also we know that at small values of r we get the correct answer. So you start with r equal to 100, 10, 1, 0.1, 0.001, etc. Okay, until we find the value at r at which convergence occurs. So first you put r equal to 100, and you can solve this with Cauchy's method or Fletcher-Reeves method. or quasi-Newton method. So the solution is 0.586, 0.586. Okay, so penalty is 26.12 and constraint is not violated. Okay, so constraint is not violated because the minus 0.586 minus 0.586 plus 5 it will be greater than or equal to 0, so constraint is not violated. Then R equal to 10, and you can use this as the starting point for the next generation. So when you use this as starting point, next point you get it 1.75, 1 plus 2y2 equal to 1.75, 1.75, and this penalty is 6.7. Okay, this is 6.7 and constraint is not violated. Okay, so minus 1.75 minus 1.75 plus 5. It will be greater than or equal to 0. So constraint is not violated. Okay, so finally you can put R equal to 0.001. So you get x6, y6 is 2.491, 2.491, and penalty violation is very less. Okay, so constraint is not violated. Okay, so you can see that this is approaching 2.5, 2.5, which is the correct answer. Okay, so comparing the sixth step with the previous logarithmic penalty example, the method has slower convergence. Okay, so in the sixth step, we are getting 2.491, 2.491. Okay, with this method. But with the log penalty function, we got 2.499, 2.499. So this is a better convergence than reciprocal. Okay. Okay, so this is the illustration of the main type of penalty functions used in optimization. Okay. Actually, many practicing engineers don't know the significance of different penalty functions. Sometimes they'll put the parabolic penalty function, which is the simplest one, to inequality constraint also. So that will not work because for inequality constraint, you have to use a penalty function which will only penalize one side. Okay, but this parabolic penalty function for equality constraint will penalize both sides. So those type of mistakes should not be made. So what to do if you have many constraints? Okay, so many equality constraints: h1x, h2x, h3x, and many inequality constraints: g1x, g2x, g3x. So what to do in such a situation? If we have many constraints, we can organize them into similar groups with a shared scaling factor. Okay, so objective function plus R1 into parabolic penalty function for all the equality functions. So all these equality penalty function share the same value of R1. Okay, that is important. And then all these inequality constraints, suppose we use the log penalty, they will share the same value of R2. Because the reason is that if you give individual R1, R2, R3, etc., then it becomes extremely difficult to track the different values of R1, R2, R3. So we have one common value of R1 for all equality constraints and one common value of R2 for all inequality constraints. So that is the only manageable way. Okay. Then we have to find R1 and R2 by trial and error. Okay. So you can see that these are all parabolic penalty functions. Okay, they converge at a large R. Okay, so these are all log penalty. They converge at small r. Okay, so it makes it more complicated. So what you have to do is that you have to simultaneously give different values of R1 and R2. Okay, for R1 you have to give values like 0, 1, 10, 100, 1000, etc. This is R1. Okay, but for R2 you have to give values like 1000, 100, 1000, 100, 10, 0.1, sorry, 0.001, etc. Okay, so R2 you give 1000 and R1 1. The next R2 is okay. R2 is 100 and the corresponding value of R1. Okay, so simultaneously you have to give this matching values of R1 and R2. Okay, and then check the convergence. Okay. So more the constraint, more is the difficulty of calculating R1 and R2. So this type of problem I'll give for assignment. Okay, so one equality constraint and the one inequality constraint. You have to write the penalty function, and with the MATLAB toolbox, you can check the correct value of R1 and R2. Look at the summary of penalty function method. Penalty function is a easy and most common method of constraint optimization. So most engineers use this penalty function method. Otherwise, they have to use the Lagrange multiplier and all, which is very difficult. Okay, but in spite of the simplicity, convergence of the solution to optima is very complicated. Okay, so the starting point must be in the feasible region or infeasible region, depending on the type of penalty used. So the penalty used is an interior penalty function like log function, then starting point must be in the interior. And if the penalty uses an exterior one, starting point can be in the exterior. Okay. Then when many constraints are used, it becomes more difficult to fix the correct R values. Okay, then R1 will be increasing and R2 will be decreasing. So you have to simultaneously try various combinations of R1 and R2. Okay, so let's just look at next topic. This is done. Okay, next topic is numerical methods for constraint optimization. Okay. So this will take some time. I think this we can start tomorrow. Okay, because this topic is totally different from what we studied. Okay, we can start tomorrow this topic. Okay, so we can stop this class now. Take the attendance.